Okay, so in this video, we're gonna still use the Laplace transform, and we're gonna do so for a slightly different function this time. So the function of which we're gonna do the Laplace transform is f of t equal to e to the at. So what's the Laplace transform of this function here? Now, if we do that, we're gonna use, as always, e to the at. We're gonna use, as always, the definition. So the definition is the integral from 0 to infinity of e to the negative st times the function we're going to find the Laplace transform of. So times e to the at dt. So this becomes the limit as n approaches positive infinity of the integral from 0 to n of e to the negative st plus at in dt. Because when we multiply those two, we're basically going to have the exponent added. So it will be negative s times t plus a times t, which is this one. So we can actually say, okay, let me just, get, there basically there is the t in common. So I'm basically gonna, bring this t here and multiply by t. So I'm gonna get negative s plus a all times t. So this is, as I said, the limit as n approaches positive infinity of the integral from 0 to n of e to, well, it will be negative s plus a all times t in dt. So if I'm just gonna rearrange and bring a here and then the minus here, just for the sake of beauty, mathematical beauty mindset, sort of speak. So as from the integral from 0 to n of e to the a minus s t dt. Now, what do we do now? Well, we solve the integral first, and then we take the limit. So to solve the integral of this thing, we have still the limit as n approaches positive infinity of, I'm gonna use this, I'm just gonna prepare to use this. Well, this one here, if you remember the integral of e to the something, so to e to the this exponent, is basically just 1 over these thing that I have here times e to the this whole thing. So just 1 over a minus s times e to the everything, so a minus s times t, evaluated between 0 and n, so those two. Now, and positive infinity. So now I'm really gonna need those brackets because I'm gonna put n instead of t and then 0. So if I do that, I'm gonna have 1 over a minus s e to the a minus s, and instead of t I'm gonna put n, so times n, minus, I'm gonna do the same, and I'm gonna put here 0 instead of t. So 1 over a minus s e to the a minus s times 0 And there we go. So now what do we have? Well, so you have the limit as n approaches positive infinity of this thing here. So this one is still going to be the same. So 1 over a minus s e to the a minus s times n, and we're gonna deal with this later. But now we're just gonna multiply everything by 0, so this just becomes negative 1 over a minus s e to, well, those two guys times 0, it's just 0. So this is the limit as n approaches positive infinity of 1 over a minus s e to the a minus s times n minus, well, this thing e to the 0 is 1, so 1 over a minus s times 1, which gives us the limit as n approaches positive infinity of well, I'm just gonna 1 over a minus s e to the a minus s times n minus this thing here, so because it's times 1, so 1 over a minus s. There we go. Now, what do we do now? Well, this thing here is fine because it doesn't have anything, it doesn't have any term with n inside, and this one in front here is fine as well because it's multiply this term, which does actually have n, but this one doesn't. So I can say that this is 1 over a minus s. I'm going to bring this little guy here, times the limit as n approaches positive infinity of, it's just going to be the limit of this guy here. So e to the a minus s times n, and then minus, because, you know, it's not going to be within the limit, 1 over a minus s. Right, what do we do now? Well, we got to solve this limit here. However, if I plug positive infinity here instead of n, and I replace n with positive infinity, I'm going to have those two things, and it will be a times positive infinity, which actually gives me positive infinity, and then negative n times negative f, sorry, times positive infinity, which is going to give me a negative infinity. So, you know, it's kind of ambiguous because I cannot say that positive infinity minus negative infinity is going to be 0. That's just, no. That's just undefined. So how do we do this? Well, let's just say that our g of n is this thing here, so a minus s times n, and our f of u is just e to the u, so e to the this whole thing, so e to the u. Now, as I said, if I do that, the limit that I'm gonna get is gonna be n approaching positive infinity of only the exponent, so basically a minus s times n. But it is the same thing if I plug just the same thing that we just said. If I plug positive infinity, I'm gonna get an ambiguous case. So what do? Well, we can, those two are not numbers that we know and that we are aware of, but there's actually comes into play in our favor, because we can say, well, fair enough. Essentially, we want this whole thing to be 0, and in order for this to be 0, we will need this guy at this exponent to be negative infinity only, so that I can get 1 over e to the negative to the infinity which basically is going to go to 0. So how do I do that? How do I get this guy to be negative infinity? Well, I can just assume that a minus s is less than 0. So it's basically going to be something, any number, I don't care what, but it's going to be it's basically going to be negative. And I'm going to call this, k. So doesn't matter what it is. It could be negative something, negative 200, negative 300, negative something. But I want this to be negative. I don't care what a is. I don't care what negative s is. Those two guys, when I do a minus s, those two have to be negative and bring me some number k negative, which is a negative number. So if I do that, and if I assume that these two guys are actually less than 0, and therefore bring me a number k, any number k, which is negative, then I'm settled. I'm fine. I'm as happy as Larry, because now I'm gonna have the n approaching positive infinity of some number negative k times n. Well, but then this will be negative k times infinity, so negative infinity, which is fine, which is actually really, really fine, because I can say so we'll have the limit for this other guy here, which just split. Oh, yeah, shoot. It's not n, is u approaching negative infinity, which I just got here, of e to the u. So this will be e to the negative infinity, but e to the something, negative will be just 1 over e to the infinity. But e to the infinity, e to raised to the infinity is something really, really big. So 1 over something really, really big will give me something really, really small, which is essentially 0 from our, calculus class. So this is 0. Then, if I'm just going to use therefore, if I just going to go back here where I left this, I'm going to have 1 over a minus s, so 1 over a minus s times this limit, which we just found is 0, happened to be 0, so times 0, minus this term here, 1 over a minus s, so 1 over a minus s. So 1 over a minus s times 0 is 0 minus 1 over a minus s. So we get 1 over a minus s. But it doesn't look, really pretty, and I like mathematical beauty. So, we have a negative sign in front of everything. I don't like negative signs, so I can just say, okay, this negative sign is going to go downstairs. So down here, the denominator is going to be negative a plus s, but I don't like to begin with a negative number, so I just, invert those and flip those and get s minus a. So essentially, the Laplace transform of e to the at is 1 over s minus a. But we've got to say with what we assumed. So with a minus s less than 0. So with a minus s less than 0. If we want to, we can say and bring s here, which is will be 1 over s minus a with I'm just going to bring s here, so a less than s. And since I like to say something is bigger than something else and not something is less than something else. I'm gonna go for my final results to be 1 over s minus a with s greater than a. And that's pretty much it. So the Laplace transform of e to the at is 1 over s minus a as long as s is greater than a. And that's pretty much it. See, Laplace transform is beautiful.